As we already learned on the axial compressors, we will also find the reaction ratio in axial turbines. And we know this reaction ratio as a ratio between the static enthalpy drop across the rotor to the static enthalpy drop across the stage. So this is the combinations between stator and rotor, and we can write them down as a functions of the total enthalpy, and it is H1 minus H2. This is the conditions at the rotor, and H0 minus H2 is the conditions between stator and rotor. And we can also write them down as a functions of total enthalpy at the inlet of the stator to the absolute velocity of the stator, and also the conditions at the outlet of the rotor. For our normal stage conditions, or when the absolute velocity remains constant or identical throughout the stator and rotor, and we will have the reaction ratio as a functions of relative velocity divided with the blade velocity and the tangential component of the absolute velocity. Or we can also use the functions of the relative flow angle, or beta, and flow coefficients. Or we can also see them from the perspective of the absolute flow angle, or alpha. The value of reaction ratio, or the amount of the reaction ratio, will have an effect to the velocity triangle, or the shape of a velocity triangle of the axial turbines, which we will discuss on the next slide. The first illustrations here represents a conditions where we have zero reactions. We can see the Moyer or entropy diagram, where at the zero reaction conditions, actually the value between beta 1 and beta 2 are similar. So that's the first clue for this zero reactions axial turbine. And we can clearly see that the velocity triangle is skewed to the left side. The next illustrations is when the reactions ratio is equal to 0.5 or 50%. In these conditions, we will have beta 1 will be equal to alpha 2, and beta 2 will be equal to alpha 1, and also C1 will be equal to W2, and C2 will be equal to W1, so that we will have a symmetrical velocity triangle. The last type of reaction ratio from the velocity triangle perspective we see is when the reaction ratio is 100%. We can see that the velocity triangle is skewed to the right side, and in these conditions alpha 1, or the absolute flow angle between the inlet and the outlet of the rotor, will have the same value, and as consequence C1 and C2 will be also identical. As previously mentioned, we know that the axial turbine can be divided as reactions and impulse turbines, or also it can be, the fluid can be gas or steam. For the reaction turbines, normally the flow passage is decreasing, as we can see here, that the flow area is decreasing across the flow path, so to say, and as it enters the rotor, in this case, the relative blade angle or relative flow angle will be relatively small. On the other hand, for the gas turbine, the impulse type, the flow area will remain constant, as the flow path will pass the constant area, and they will have the same value of A1 and A2. This impulse type of axial turbine normally being used for steam, and the reaction type is normally for gas. On the other hand, the steam turbine normally has a pressure ratio up to 1000 to 1, and the gas turbine is normally as low as 10 to 1 pressure ratio.